This episode is sponsored by RV Magnetics.
Hi, everybody, and welcome to CW Trending. My name is Jeff Sloan. I'm editor-in-chief of Composites World, and I'm joined today by senior editor Ginger Gardner. Hi, Ginger.
Hi, Jeff.
Ginger is going to talk a little bit about some research she's been doing on sensors and sensor integration into composite parts and structures. So we've got a presentation here for you, and we'll let Ginger run through that, and we'll have a discussion as we go about some of the technology and what Ginger sees happening in the space. So Ginger, I'll let you take it from here.
Great. All right. So we're doing something a little different today. It's not your normal PowerPoint. This is a Prezi, which I prefer. Okay, so we'll start off with why use sensors. So if you can see this figure on the left-hand side, that's from a sensor manufacturer called Kalo in Finland. And I think that diagram shows really well why we want to use sensors. So when we talk about optimizing parameters, we can look here at the Cosimo project. You can see up here that when they were able to do this and look at how to digitize the process, they were able to make that press a smart press. So we want to be able to operate equipment with the best parameters, temperature, pressure, have the equipment start and stop based on what the materials are doing and when the parts are finished. We can also make the equipment adaptive. So you can see here an adaptive press by Schuler. And when you see the rainbow colors there, that's just to indicate that they were able to get a difference in pressure on that preform in the RTM process based on the geometry and the materials. And then we can look at smart injection. So if we have sensors monitoring resin flow, we can effectively turn the inlet port off when the flow reaches across the whole part. And so again, it's looking for efficiency and reduce cycle time. Some of the cycle time reductions that we've already seen achieved by these sensors are as much as 25 to 50%. So that's not insignificant at all. One of the things that we're looking to do as we move forward in composites is digital thread and digital twin. So thread would be the line of data from design to manufacturing to end use and end of life and all the way back again, right? And digital twin would be the individual parts. So if we look at a digital twin here of a pressure vessel, say a hydrogen tank, then the kind of data we're pulling in are what's going on as we wind it, what the tension in the fiber is, what the strain in the different layers are from the liner all the way out, what the curing is, what the strain looks like as we go to proof test it, and what it looks like as we do certification testing and cycling, and what happens as we fill the tanks over the lifetime. So this is really important, and we have to have sensors to gain that data. Also, what I see coming is that we're reaching this next gen window where we can do things we just haven't been able to do before. So in this example, Royal Hoosman is a yacht manufacturer in the Netherlands, and they worked with Common Sense, who supplies fiber optic sensors, to put these sensors all along a CFRP rudder. And when they went to do the sea trials on the rudder, they were able to see all the load on the rudder. So the reason they did that is to validate the model that was used to design the composite rudder. But it turns out as they're doing the sea trials, they're noticing, you know, on an 80-meter yacht, we can't really feel what's going on in the rudder, but you can see what's going on. And so they put an amplification and a haptic device where they can now feel what's going on in that rudder. And that's just a whole new way of thinking about intelligent structures and how to make them communicate with us. And I think it could open up a lot of windows. One of the other projects that I've written about is the Optolight project, and that was done at AZL Aachen in Germany. And what's intriguing is that through having these sensors and through watching different processes for this part, we were able to take a thermoset substrate and overmold it with thermoplastics. And combining those two materials is something that we don't normally think about doing, but sensors, they just open up new possibilities for us. So we're going to move on now to sensor types. So Jeff, you and I talked about the fact that in injection molding, you guys, that was what you did before you came to composites. That industry has used pressure and temperature sensors for decades, right? And
Yep.
So, and we do that in composites too. We have Kistler pressure and temperature sensors that I've written about that are used in molds. We know how to use strain gauges and thermocouples. What I'm writing about in these articles and blogs and this presentation today are where we're going beyond that. So these are sensor technologies that allow us to pull temperature, pressure, and other data together. And then we have these sensors on this side, which I call multi because they're different technologies that let us go beyond just temperature and pressure. So we can have different kinds of data that we pull. I'm not going to talk about printed sensors today, but that is something that we're going to be moving into. And that's just a whole brave new world. This that you can see down here below are some examples of some of these sensors and what they look like. And now we'll look at actual applications.
So Ginger,
So one of the, oh yeah, go ahead.
You know, especially in aerospace, process is qualified. The process is qualified. So especially with autoclave cure, even out of autoclave cure, materials have to be at a certain temperature for a certain amount of time under a certain amount of pressure in order to be deemed certified or qualified by the OEM or the certifying agency or whoever it is. So the use of sensors is a departure from that, because instead of saying we're going to run this at a certain temperature and pressure for a certain amount of time, we're going to say we want to get the material to this level of response or performance according to the sensors, which is a different environment, especially for aerospace, as I said, but it's a different way of thinking about how we do process control and how we manufacture structures. Do you see, or have you gotten a sense for what the OEM community thinks about this, and are they receptive to going down this path?
I think that as an industry, we don't have a choice. I think that the sensors are opening doors and providing solutions to problems that the OEMs are discussing. For example, when I wrote about RTM parts in our supplement last year, and I wrote about the work that the CTC in Stade is doing, they have now completed that transition I talked about. They had about a dozen tier suppliers that they were switching from prepreg to RTM in order to meet rate. So, Airbus has announced rate 65 coming up. After that will be 75 and 100. And in order to meet rate, you have to have shorter cycle time. So one of the things they talked about with the RTM is they were able to get fairly short cycle times, but they're still using RTM6, which is a one component resin. And I said, well, we have all these snap cure systems that are two component that we could go even faster. And he said, yeah, but the problem is, that A to B mixture has to be right all the way through at every single microsecond, at every single part. And we don't have a good way to prove that. Well, with sensors, we do. And so I think that the OEMs see that benefit. They're already talking about sensors they can put in different pieces of equipment. The multifunctional fuselage demonstrator, they're looking at sensors and certification. They're looking at SHM because the OEMs know that we need to cut time. There's a news item that we posted recently on Clean Sky 2 is moving forward as clean aviation. And what the director Axel Krein talked about is that by 2050, we want to have these zero emissions aircraft that are going to be new coming out in 2035. We want 75% of the commercial fleet replaced between 2035 and 2050 with zero emissions aircraft. Okay, well, the only way to do that is to make certification easier and more, quicker. So I don't think we have a choice. And I think, Axel talked about they're working with EASA through that program. So I think, yes. Is it here right now? No. But I do think everybody sees the value of it. And it's better than a legacy recipe, because what you're now certifying through your digital twin and your digital thread that you have is that you understand what is in the part, what the TG was, what the cure cycle was, what the degree of cure was. So yeah, I don't think that's going to be the hard part. I think the hard part is going to be getting the industry up to speed. I think that's going to be probably more of the issue, is everybody familiar with how to use these sensors and making it work.
Yeah, it is a pretty big departure from the norm for sure.
Absolutely. Yeah, and it's not it's not a no-brainer. I mean, you can look at what I'm going to present here and see the value of it, but to make it work day in, day out, it's going to take some effort for sure. Absolutely.
Yeah.
So as I go through these case histories, I will have names of companies that I'm pulling the images from. But just to let you know, we've written about a lot of different companies, and these aren't the only suppliers. So when I talk about dielectrics, I have blogged about Lambient. We're getting ready to blog about Netch, but most of the images you'll see are from Synthesites. The same is for fiber optics. I have blogged about Common Sense. I'm getting ready to blog about Photon First. But Luna's, really well known, and they do a lot of work in this area. And that just, these aren't the only suppliers. They're just the ones that I'm talking about here today. So for dielectric sensors, what it's actually measuring is the electrical resistivity in the resin. So it's actually part of the material state, right? And you can see in this graph, you have resistivity here, and then you have the temperature here versus time. And what you can see is we actually get to see a lot. We can see when the resin's arriving. We can see the viscosity changes. We can see as the resin gels and reaches its glass transition temperature, its T sub G, that we're reaching the end of cure. And so all of this is incredible. We have a lot of visibility into what's going on. To give you an idea of what these look like, so that's the in-mold sensor right there, and it will be in contact with the resin as it's going through the injection or infusion. That's a disposable sensor that can go on the part. And then you have to wire it, you have to have a wired connection from these sensors into the data acquisition, and then it feeds into the analysis tools, right? So when we look at this data and we're measuring this data, what it allows these companies to do is then take that and do real-time estimating of viscosity, T sub G, and degree of cure. In some of the experiments that Synthesites has done, some of these projects it's done, it was able to compare its estimation versus the DSC on demolded samples and parts. And DSC is just one of the common lab techniques we use to make sure a part's cured or resin is cured. And what they were able to find is that the delta T, the difference, is less than 2 degrees Celsius, about 2 degrees, which is pretty impressive. So this real-time estimation works, right? They're pretty accurate with it. And they've been able to show that they can open and close feed lines, that they can stop the cure cycle based on what they're doing with this T sub G estimation and degree of cure. Now, why is that important? Well, they've already demonstrated they can reduce the cure times on RTM6, which is kind of the current state of the art with RTM in the aircraft industry, and they've been able to drop those by more than 30%. That's really impressive. Some of the examples that I pointed out in the blog I did on this was when Bombardier Belfast developed this infused wing process, they part of their more recent development in the past few years was to look at using these sensors. And even though they're injecting and in the autoclave, they're able to pass those sensors through the autoclave wall. And it was pretty impressive what they were able to get on that. Some of the other projects that I think are impressive are with the wind blade manufacturers. And what Synthesites is now claiming is that for a given production line, they can drop the cure time by 1.5 hours, which buys you at least one blade a month on that line, reduces your energy, and they claim you can get a return on investment in the system in about 4 months, which is pretty impressive.
Wow.
Another use of dielectric sensors is not just in liquid molding, but in prepreg molding. So one of the projects they did is working with fiber metal laminate. So that would be glare, Glare, where you alternate the aluminum and glass fiber epoxy prepreg as a fuselage material. And they were able to drop that cure time by 50%. And then when I talked about Optolite, what's interesting to see is that it's all in one machine, right? So they do the compression molding on one side of the thermoset, and then they swivel that platen and they push it into the injection molding site. So by having that visibility into the process, they can tell when to stop one and keep enough latent reactivity that they can turn around and use that to attach to the polyamide when they go to overmold. And so that's, it's key if you want to have these new materials and you want to make sure that you have the attachment and the bonding optimized, you have the data you need to do that. So heat flux sensors I wrote about this year, they're similar in a way to dielectrics. They're pulling actually what's going on in the whole system during the cure process. So they're monitoring the heat flux in the system, as the reactions are taking place. And they have an internal temperature sensor so that they can subtract out what's going on in the mold. They just want to see, obviously, what's going on in the materials. And you can see the curve here. And it's somewhat similar to what you get on the dielectrics. Just like in the dielectrics, they've been able to show they can reduce the cure cycle on RTM6 by being able to see the into the process. Some of the other things that I think are impressive is the work they've done that was recognized by JEC with snap cures, and that was a Huntsman epoxy. And then this project that I wrote about is for landing gear and being able to just, if we want to do these big structures, GKN realizes that they just need to have a lot more information. So when you talked about OEMs, I mean, here's a big tier one, and they know this is what they have to do going forward. So they're already doing this work to prove it out and make sure they can do that. Right now, these temperatures pull heat flux and temperature. TFX, the company that's working on the sensors, they're looking at developing the ability to pull pressure within the same sensor as well. So fiber optic sensors have been developed in composites for decades, mostly for structural health monitoring. The way they operate is a little bit different. It's a glass fiber. We all know what fiber optics are. But what they do is they etch this grading in there, and the grading marks are equidistant. So what happens is normally when you pass light through, it has a reflected wavelength, and that leaves the rest of the spectrum to be transmitted through. But when you apply strain or temperature, it changes that spacing. And so the wavelength that gets reflected changes, and you can see the change. So what is interesting to me is that because you're using a fiber optic line, you can put 20 to 40 of these FBGs on a single piece of optic fiber. So you have a lot of sensing points. It is a connected sensor, just like the dielectrics are. You have to connect into the edge in order to be able to interrogate the sensor. But Common Sense, what I blogged about earlier this year, has developed a patented connection. So you can see the prototype of their edge connection here, and then this is the surface connection. So they're working on trying to make that more user-friendly for the composites manufacturers and the people that operate the structures. One of the other things I find interesting is that they've already shown they can automate it. So this is work by Photon First in the Sucos project, which looked at high temperature composites. So that's where we're looking at BMIs and cyanide esters and thermoplastics. And you can see on the AFP head they used to make all the samples, 7 of the lanes are for tape, and then the 8th lane was what they used to lay down the fiber optic lines. And you can see here the curves. They're not exactly the same as what you get off a heat flux or a dielectric sensor, but it's somewhat similar, and it's giving you changes in the light that's coming through, in the temperature and the strain that are in the structure. One thing to note is you can monitor strain and temperature with these, but they have compensation mechanisms so that you just pull one or the other, right? But it is nice in that you get a lot of information.
And Ginger, the Common Sense technology is wireless, right?
No, Common Sense is just like all the other fiber optics. There are wireless ones coming up, though, and I'm going to show you those.
Okay.
So one of the things that I find interesting about fiber optics is, like I said, all of this data that you can get. So you're looking at strain effects during the winding on the different layers, during the cool down and the curing, as you're temperature testing, cool, dry to hot, wet. Being able to do load and deformation analysis. These sensors are being used in all kinds of structures that aren't even composite, in roads and bridges and buildings. And one of the reasons they do that is so that they can look at what happens with load and deformation of the lifetime of the structure. Also, like I showed with the rudder, they used that for design validation and validation of their FEA. But one of the other things that I find interesting is you can use these for flow monitoring. I wouldn't have thought that you could use this kind of sensor for that, but basically there's a change in the strain as the resin comes through, and/or temperature, and so you can actually see the position of the resin. And then when you look at these large civil engineering structures, this is actually a composite lock gate, and so that's in a lock gate for a canal in the Netherlands. And this gives you an example of how they made the lock gate with the fiber optic in it and had the connection so that they could do the interrogation. And what they wanted to see again was load and deformation analysis over time. Now we're coming up to these are also wired sensors. These are ultrasonic sensors. So this is a news item that I reported in September, and this is a project called Cosimo. and it's about composites for sustainable mobility. It was led by Forcia, and they're looking at kind of a Frankenstein challenge part for a battery box cover for an electric vehicle. And what they did was design it with a lot of different geometry and metal inserts, carbon fiber inserts. They were using a non-woven glass for sustainability reasons, and they just wanted to see if they could monitor the process and understand the process. It's a different process. It is what we call thermoplastic RTM. So they took a caprolactam monomer and they polymerized that in situ during the RTM to become PA6. So that's nylon 6, and that's the part you end up with. So obviously, it's really important to, number one, make sure that you know that that monomer got into all the crevices and the different geometries. So if you see here, this is the sensor grid on the upper mold and the sensor grid on the lower mold just for the ultrasonic sensors. And that lets you see what's going on at every different part, right? Where the resin is going and how it's polymerizing. The sensors that mostly were used out of a network of 70, most of them were these ultrasonic sensors. And these were developed by the University of Augsburg. And I'll be doing a blog on that pretty soon. And what I thought was interesting is that I had never heard of ultrasonic sensors, but Marcus Saus at the University of Augsburg was telling me that these are really common. They're used in industry all the time. The problem is that the ones that are commercially available max out at about 150 degrees C. And what they needed for this process was a little bit higher because of the thermoplastic. So they were looking to take it up, I believe, to 300 degrees C. And so they just redesigned an ultrasonic sensor to where it would work for their process. And then they also used some DEA sensors in there and some Kessler temp and pressure sensors. But he said these ultrasonics are cheap. And like in a normal part, you wouldn't use 7D. But for this project, they did because they wanted to develop a digital model. And so that's what they did. And by doing that, they could show that it met the polymerization rate they needed, and they could produce the part the way they wanted. Now, what's interesting is that DLR, the German Aerospace Center, their Center for Lightweight Production, which we call ZLP, they're now working to adapt this kind of process, this methodology for infusion processes. So this was a pretty quick injection because it was thermoplastic, but in infusion, it's a slower process, and they feel there's a lot of benefits to be gained. And then the other thing that I find interesting, which I'm going to blog about, is Dr. Saus at Augsburg and Fraunhofer and DLR are working together. And what they're doing is they have this new organization called the AI Production Network, and they have a new building going up in 2022 where it'll be kind of a mad scientist lab for sensors and AI. And you can work with them to see how you might be able to do that in your process and what kind of sensors would work and how that might be adapted. So I think that's going to be just tremendous to have that capability. Now we get to the wireless. So this is the first of the wireless contactless sensors that I am going to talk about today. So I've blogged about RV magnetics this year. It was one of our top 10 blogs this year. And it turns out the technology I've written about for a while. So years ago, I wrote about AvPro, and AvPro is in Oklahoma. They're here in the US. And, we talk now, like you said, we're talking about using sensors and trying to get away from legacy time temperature recipes, but instead going to what we call material state management. Well, Tom Rose at AvPro was beating the drum for material state management decades ago. I mean, before we had any of this idea we could do it, he was saying we should be doing it, and that we should be basing our cure cycles on when the resin's cured, when the part's ready and has met mechanical properties. What AvPro's been doing is maturing this technology. They have an SBIR with the Air Force, and they're on their phase 3 right now. And this was for repair. So what they were doing was using what they call a thermopulse sensor. So it's 3 different magnetic microwires. And those 3 wires get put into this sensor, and they were putting it in the bond line of a repair. So a composite bonded patch repair is basically new materials on an old structure, and you're adhesively bonding them together pretty much, right, while you cure the patch. So they wanted to see that adhesive line or the line between the old material and the new saw the temperature it needed so that you could prove you had a good repair. And they've been able to do that. They've been able to show they can put this sensor in that repair line and it doesn't affect the mechanical properties. They can put it in an adhesive bond line. It doesn't bother it in any way. And they can read the temperature through a thick laminate of carbon, which is pretty impressive actually. So this year, what I talked about was RV Magnetics. It's a new company. And they're in Europe, what they've been doing is using the same microwire technology, which it's a technology that's been around for decades, and it's based on this metallic alloys drawn into a wire that are magnetostrictive, right? So they respond to a magnetic field. They can constrict and expand. They respond to their environment, and they'll emit a magnetic field based on what's going on in their environment. And so what they do is they take these really thin microwires, put a glass coating on them, and they can measure 2 out of these 3 simultaneously: temperature, strain, and magnetic field. And it was funny when I said, well, AvPro's been able to, since wireless, do interrogation without contact through this thick laminate. And they said, oh yeah, you can't even find these things in a part unless you have our interrogator. They're tiny and they don't bother the part at all. So what they've been able to do is their interrogator sends out an electromagnetic field, and it causes the sensor to send back the data, right? So they have an excitation coil and they have a sensing coil, and then that data gets logged back to the computer, and you can watch the change in temperature, the change in strain or magnetic field as the part's being cured, tested, etc. One of the things that I find interesting about this, there's real potential here. It kind of like fiber optic sensors, you can take just a gram of this, unique metal alloy, and they have all different kinds, and they draw it out to make 1 kilometer microwire, and they've already shown that they can put it in fiberglass rebar through the pultrusion process. So, the idea of having fairly cost-effective sensors that can go, into long stretches of pultruded products is really fascinating. I think that offers some, unique potential there for the future. Also, the way you can tailor the sensors. So that's one of the things that RV Magnetics works to do. It would be normal if you're going to do cold dry to hot wet testing that you'd have this kind of a temperature range. But then if you wanted to put a sensor in the human body, which is what they've been doing because they work outside of composites as well, you don't have a big change in temperature, but you need, really high resolution. You want to see really minute changes. So there's a lot of flexibility in these sensors and what they can do.
So Ginger, quick question. RV Magnetics measures 2 variables simultaneously. Is that a function that is defined in this wire itself, or is it just the interrogation? So your interrogation says, I want to see temperature and strain this time, and next time I want to see strain and magnetic field.
From the way I understand it, the way I blogged about it, it's a little of both. It's so you can see here what AvPro did is they used 3 microwires in their thermopulse sensor because they're using the Curie temperature principle of physics, so that they have kind of a max temperature ceiling and they have a built-in calibration. And so RV Magnetics is kind of looking at the same thing. It's how you design the sensors using the microwire, but it's also how you interrogate, because like I said, when you do a fiber optic sensor, you need to be able to compensate if you just want to pull one or the other, right? Temperature or strain, because they affect each other. And it's the same here. All of these 3 affect each other. So it's part of how you do the interrogation and the analysis. You have to compensate to isolate what you're looking for.
Okay.
And those compensation techniques are really well known for fiber optics and obviously for these sensors. So the last sensor type I want to go over is the newest one for me. And this is, again, Kalo in Finland. And what they've done, this came out of the ceramics industry. The CEO, that's where he got his PhD, is in ceramics. And what it is, it uses a magnetic field to interrogate without contact. So this is an example of the same probe that you can see right here that you would put in a liquid. And this is the plate that they would attach to a pipeline or a resin mixing vessel, etc. And if you can see the sensor, it will read through any kind of non-metallic, right? Any kind of coffee mug or plastic cup or a laminate, composite laminate. And what they do is they're measuring the permittivity and the ion viscosity of the liquid. So again, that's looking at kind of the material state, right? And what you can see here is by graphing these 2 against each other, you characterize the materials. And here you can really characterize them very finely. Why would you care about one gin versus the other gin? Well, it turns out one of their customers manufactures gin, and they use like 7 different botanicals, and they want that gin to always taste the same, right? They have this perfect gin, and they, through using these sensors, can benchmark that process. This is the process for that perfect gin. And then once they do that, they can then monitor to make sure that that's what they're doing. So they can benchmark it and see how each batch is varying from that benchmark. So this was for a paint manufacturer. They work with an epoxy manufacturer in Finland, and they can monitor epoxy hardening with time. They can monitor all kinds of processes. Here you're looking at what happens as wine spoils. This is where the wine stacks up in the beginning and how it changes. So, I mean, it's amazing to me what you can do. So again, we were talking about, the RTM and mixing. So if you look at all of the things it can look at, it monitors polymerization, it monitors cure, viscosity change. We degas resins all the time. We need to know, how far we could stop. We don't have to degas for 6 hours. If it's done in one, then stop.
Right.
For mixing and homogenization, so they work with like milk manufacturers to make sure the milk's homogenized. Okay, well, that's the same principle as mixing A to B in an epoxy. And if you have these sensors, which can read through, and you're infusing, you can tell if yes, the liquid is within my parameters, or no, it's not. And that could solve some of the problems that we see. You're looking at how to monitor chemical reactions and impurity, sedimentation. When we make ceramic matrix composites, these are really important things to understand: nucleation and crystallization. So these are other things that we can look at. And also, we look at crystallization in thermoplastics. Agglomeration is something we look at with nano. Whenever we do nano additives, agglomeration is a big problem. One of the other things that I find fascinating is they go beyond just the permittivity. They call it a collo permittivity and the ion viscosity, and they have 6 other variables that they track. And he said the best way to give you an idea of what that does for you is just to show you how fine the fingerprint can get, because they have so many variables that they're monitoring. And the last is where we're going to end up with sensors. So one of the things that the CEO of Kahlo told me that I thought was really fascinating when we were talking, he said, so many times what we're doing right now is we're running along a highway to make a part. And for a lot of people, they don't have any sensors going on and they're running blind. But for others, maybe we're pulling a data point at the beginning and at the end, or every 10 minutes. Okay, imagine running down the highway and you only open your eyes every 5 minutes or every 10 minutes. He said, it's just not where we need to be. And that's what I see changing, is that we'll have real-time visibility. We'll be watching what happens to the process, and we'll be using that to change the equipment and the materials in situ, to increase the efficiency and productivity that we need. And we talked about digital twin. This is a blog I did on Nebumine software that works on digital twin. So, this allows us to have the data and the temperature and the pressure through the part. This, certification, you asked the question, that's, really key. We need to have this kind of data. I think it'll make certification easier. I think it'll give us a lot more justification for what we're doing. And we talked about, having this digital thread and having these structures that not only just tell us when maintenance has to be done, but communicate to us in whole new ways and feed back into the digital thread so that we can have better designs and have better processes. And then, what we could see through Kahlo is really this fingerprinting, the granularity of data. I just think being able to really understand the materials and having that granularity, and also in the process, it's just going to increase our understanding. I think it's going to let us do things in the future that we probably can't even conceive of right now.
Well, you could understand immediately for incoming material. The very first thing you do is you want to characterize a material and make sure that what you ordered is what you have, and what you have is what you need. And being able to fingerprint that and know that you're starting your process with a material that meets the specs is huge.
Oh, I could tell you stories. My husband's a boat builder, and it's not uncommon to have a resin and all of a sudden it's acting funny, and you ask, did anything change? No, nothing changed. And then you find out later, well, one thing changed, just a little bit.
Yeah.
And it turns out it changed everything. It made the infusion much more difficult. So Yeah, I think that's huge. I agree with you totally. But also, as we learn, the idea is that as we have sensors in the process and they feed into these data repositories, that we use AI and we learn quickly. And we see patterns that we wouldn't have even maybe noticed. Um, but the more parts we make, the more it sees. And yeah, I think the knowledge we're going to gain is just huge.
So all the tech, I mean, you reviewed a bunch of technologies that are either out or being developed. Are there, I don't really want to pick winners and losers, but I'm wondering, are there any you see that are particularly promising, or is there like more flexibility available through one technology than another? Or does it just kind of depend on the application and the structure? And
I think it really depends on, as always with composites, I think it depends on the part you're making, the materials you're using, the process you're using, and what's going to work for you. I've shown you that there are a lot of different ways you can get to flow monitoring and cure monitoring. There's really no excuse for us to not be doing that anymore. But some people didn't want to have a sensor that had to contact the resin. Some people didn't mind, that didn't bother them. Others don't mind the wired connection. Some would prefer to be able to work wirelessly. Some sensors are affected by by a magnetic field and others aren't. So they're and then you have temperature issues. So there are a wide range of needs. And I think that's where I see a need right now is we need companies that know how to do this, that understand the sensors and the software. I mean, you saw all of these different types of sensors where there are just as many types of software out there. There's Platane, there's Siemens, there's Nebumind, and that's just scratching the surface. There's so many different kinds of software that can help you take that data and make your digital twin and your digital thread. So yeah, we need more companies that have knowledge here and experience here to help people integrate all of this.
yeah. Okay. Well, very good, Ginger. Appreciate it. Thanks much. And we'll look for the feature on this coming out in the next few months, right?
Yeah, that's right. Next year we'll have a feature on this. So yeah, absolutely.
All right. Thank you much, Ginger. Appreciate it.
This episode is sponsored by RV Magnetics.